Good morning. I'm Dru Crawley with Bentley Systems in Washington, D.C. I'm delighted to be able to be here today at the IBPSA LATAM. I wish I could be there with you in person, but last-minute family obligations prevented me. Today I'm going to talk about impacts of climate change and urbanization on future building performance. This is part of ASHRAE's Distinguished Lecturer Program. This is a kind of a unique program where they provide lectures with a number of ready-to-go topics for 80 different speakers. So the chapters can pull speakers in on topics that they're particularly interested in. One of the things I like to do is start all my presentations talking about why energy in buildings is important and what the difference is. Worldwide, buildings are about 30% of energy use, and that's been increasing with time, but we still 50% of our energy use is for industry. But if you go to the third and fourth bars, they're two of the larger contrasts. China, which is about 20% for buildings today, but that's more than doubled in the last 20 years. Huge amount of construction gone on there, more energy use. And then Hong Kong, kind of the opposite extreme, where buildings are responsible for about 65% of energy use. And industry in China at 70% and Hong Kong under 5%. So two contrasts in how different economies work. If you go to about the fourth set of bars, you'll see South America, IBPSA, Argentina, Brazil, and Chile. And Argentina about 30%, pretty close to what the normal or the average for the world is. Brazil a bit less at about 25%, and Chile a little under 20%. So it kind of depends on how the economy, where the energy is being used in the economy. In the US, the last bar is we have about 40% today of energy use in our buildings. And that has grown quite a bit over time. If we were to look back at say the 1960s, the industry part would be well over 50% and buildings under 20%. And that's partly because we built a lot of new buildings. The population has doubled in size in those 50 years, and it is changing. Split about half between residential and commercial. Both have been growing over time. But let's talk about some of the pieces of it. And one of the reasons I like to talk about this is to explain that we have to be able to look at the entire building. We can't focus on a few of the high proportion energy uses such as heating, water heating, cooling, and appliances. That's no longer enough. I mean, televisions in the US are at 3%, computers over 1% today, and other uses, that category there. Now, if I were there in person, I'd hold up my cell phone and say, this is one of those uses that 25 years ago that we just did not have. Commonly, everybody have a cell phone. So that sort of small appliance that is drawing more energy has crept in. On the commercial building side, of course, there's no typical building. If we were looking at a supermarket, for example, we'd be looking, the refrigeration would be up over 50%, and lighting and cooling would be about 20% each. So much smaller. If it's an office building, it's probably cooling, lighting, ventilation, office equipment driving it. But look also at that office equipment and computer, almost 13% total in commercial buildings today. It's grown quite a bit. But again, there's the other uses, almost a full third of the commercial building energy, and that's transformers and medical equipment, elevators, escalators, laboratory fume heads, all sorts of things going on in our buildings today. But they're small uses. But altogether, we need to look at the entirety of that if we're really going to make our buildings more efficient and decarbonize. So, to the topic at hand, climate and weather. Well, they're not the same thing, although people sometimes use them interchangeably. Weather's what's happening right now. It's the temperature, the wind speed and direction, maybe whether it's cloudy or not, how humid it is, whether it's raining, atmospheric pressures. What's happening right now? Climate, on the other hand, is a composite. Over time, usually a number of years, meteorological circles, they do what they call normals, which are a 30-year snapshot. At the end of a decade, they'll update the normals. So we have a recent update through 2020. But it is looking at not the average, but the prevailing conditions for that. So when we talk about weather and climate, we need to distinguish which we're talking about. Weather is very variable. The green line you see going across there is solar radiation, and you see it kind of varies a little bit. Well, there's, and quite frequently. This is from National Renewable Energy Lab outside Denver, Colorado. And you see the solar drops off in the afternoon. Well, this is an August day, and there on the east side of the Rocky Mountains, it tends to cloud up in the afternoons. It may not rain, it usually doesn't, but it often clouds up, so we see a drop off in the amount of solar. We see the temperature and the dew point varying throughout the day, but also the temperature. And you see it varying quite frequently. And usually when we're talking about weather and climate data, we don't have this resolution. This is about at 1 minute of data. And this is just about 12 hours of data. One of the interesting things the New York Times has been doing recently, in addition to the regular reporting, is looking at how much hotter particular locations were. And you'll see there, this is for Florianópolis, and 2016 was the global hottest year. So how much warmer was it? And on average, it was about, in Florianópolis, it was actually about a half a degree below normal. And you can see some of that happening there in April, May, June, where temperatures were below that gray area, and that's the range of normal temperatures. But you also see throughout the summer, even July, August, September, October, and then the summertime in November, December, January, we're seeing going above that normal range quite frequently. No records were set, but in many locations, when I pull up the same information, you'll see record high temperatures in the spring and the fall. So this was kind of an unusual year for Florianópolis. For 2019, which so far is the second hottest year, we're seeing that Florianópolis actually was warmer, that on average it was about a degree above normal for the entire year. And you kind of see that where the not very many hours or days that are going below the gray anymore. We're seeing consistently above that. So that's kind of what you see traditionally when you pull up some of this data, looking at how it compares globally. So this is an animation of global temperatures, but the mean annual temperature at various locations. And you'll see when it started in 1850, we kind of had gray spots in many areas. By the 1880s, we're getting good data throughout the world, with the exception of Antarctica and a few places. And you'll see it changing. On the right, you see a temperature anomaly bar, and that's versus the temperatures in the 1950s to 1980s, which has been used as kind of a baseline. But then you see, once it starts to get, we have some high temperatures in the 1940s, 1950s and 60s cool off a bit. Nothing's really that out of range. We see occasional hot or cold spots through there. But by the time we start to get to the 1980s, and you see the line going across the bottom there, we're consistently above that anomaly from that range. And so by the time we get to the 2000s and even to the recent years, as it slows down here, you're seeing we're getting consistently hot temperatures almost globally, not entirely for every location. And that's why for 2016 you see a little bit cooler there for Florianópolis in that region of Brazil, but by 2017, 2018, it's warming up again. So it's not consistent change throughout the world, but it is available. For example, here's 2019, the next year. And in that case, southern Brazil was actually quite a bit warmer there for many locations. North America was actually about normal. Big swaths of Africa were above normal, and then Australia, of course, was as well. And that was one of the years that they had a real problem with with wildfires in Australia. One of the other indicators we've seen is North Pole sea ice, and one of the things that's happened the last few years is during the winter the sea ice has, or the temperatures at the North Pole have gotten above freezing during the winter. It's never happened before. And what you're seeing here, the little bar chart on the right, starts at about 25,000 cubic kilometers of ice, and by 2017 has dropped to only 15. So we've lost 40% of the ice in that period. We've seen other extremes. You see Australia there in the middle, North Pole on the far left, showing temperatures in the winter that are 40 degrees above normal. Or U.S. East Coast, this was a January day where we're seeing temperatures 10 to 15 degrees above normal throughout the coast, but then a big swath of cold in the middle of the country as well. Temperatures have changed over time. Global annual temperature from the 1940s, we're already seeing about a 1.2 degrees, already seeing that in the data that we're looking at today. And it's also changed. 2020 was quite hot in Siberia and Russia. There was a heat wave again in 2021 in Europe and parts of the Middle East and Northern Africa. And then 2022, again, a cold streak there in southern Brazil, but much of of Europe and Asia were actually quite a bit warmer. So let's take a look at what's been happening in Florianópolis. This is from a great data source, Berkeley Earth. You can go and look up any location, but some of the data here, it's not 1758, sorry about that, it's about 1830. There's some data that being recorded there. You see gaps in there. But from about the 1880s on, you're seeing consistent temperatures. And then the temperature is continuing to rise. So from that baseline period of 1950 to 1980, we're already seeing about a degree increase in Florianópolis in the record, not predicted. The other thing that's happening, looking at the hottest and coldest months, these are the ranked coldest monthly and average annual values, and the years that had the coldest month. You see only 2 years, 2016 and 2017 there in July, where they even rank in the top 5. None of the other locations have that there. On the other extreme, the yellow was indicating which locations or which years in the last 20 years were there. So look at that. All the yellow that's happening, all the various months, many of the hottest months are from the last 20 years. And that's pretty consistent if you look at different locations. If you look at the high and low temperature trends, you'll see the high temperature is trending warmer, about a degree there. But the low temperature, we're seeing something on the order of more like a degree and a half. So that's consistent with what the models are predicting. Let's talk about building simulation and its aspects for climate. If you're a building simulation, this should be a book on your shelf. But I'm going to talk specifically about the weather and climate chapter and what information there. But the good thing about this book, it talks everything about individual simulation of components and pieces and systems all the way up to urban scale. So it's got a good combination of things for that. Within that book and that chapter, it talks about climatic data requirements. So if we're doing an energy design and compliance analysis, we can do typical full year data. If we're looking at unconditioned or semi-conditioned buildings, maybe typical data is not enough. We'd probably need warm summer multi-year data to begin to look at it. If we're doing equipment sizing, selection, we need design day or short period, and so on and so on. So daylighting, we need luminance data, obviously. And so there's lots of things going on, different ways of doing simulation and what we need to be able to do with it. But one of the challenges we have is that some of the weather data elements are actually quite easily accessible and others are not. So dry bulb temperature, that one's pretty easy. Anytime you have an airport or even a meteorological station, there's big opportunity to get that. It's easily available. Humidity, somewhat similar, but then we look at solar irradiance and solar illuminance. Solar irradiance is not typically measured. The stations for which most of our weather data come from are from airports, and their main concern are wind speed, direction, humidity, and temperature, and that's really the key. So there are very few well documented or available climate data sets that have measured solar data, but I will tell you about some in just a minute. So I'm not going to go through some of the others, but one of the things to be concerned about is making sure that you have that data available. One of the interesting thing that's happened over my career is that weather data has become increasingly available. That when I started, we had weather tapes. They were physical tapes of 9-inch reels that you put on a mainframe computer to be able to look at them. And that was a real gem of the time, as good as gold, because there were not that many, even in the U.S. Back at that point. But in the past, even back then, the weather data was only available from the ground observing station, these weather stations at the airports and a few other locations. Good data, temperature, humidity, wind data, variable due to terrain, site obstructions, urban canyons can change quite a bit. So wind data is not exactly terribly useful. Solar data is rare still. There are a few global data sets, and they're set there more to set the baseline to help calibrate other data. And that leaves most of the rest of the data is kind of incomplete and limited, so you're going to have to be looking for sources to supplement that. Now we have remote sensing or satellite data and data sets that are extending for many years for that. The interesting thing is quite good, average. The ASHRAE Climatic Information Committee, TC 4.2, has been working with NASA with one of their data sets for about 15 years now, and they're able to replicate the design conditions in the ASHRAE handbook within about a degree or half a degree, which is pretty amazing given that it's from space. It gives comprehensive global data and a relatively decent grid. The good thing is that grid is getting smaller. The European data set, for example, is at a 30-kilometer grid now, and NASA's data set is a bit bigger than that, but they're looking to go down in that range in the next year or so. And you don't have to have a ground station. That's probably the best thing. So these large areas where we don't have stations, we can get data. The data sets are actually quite good in almost real time, usually within a few hours or days. But we can't use that data raw. If we're doing simulation, we have to make sure we have a complete period to do the simulation with and make sure we have all the data we need. So we have to do the data filling. But if we need design conditions for doing equipment sizing, we're going to have to do some statistical analysis. Design conditions been traditionally where ASHRAE has done a lot of work over years, and they've done trying to create new ways of getting there. So used for design sizing of our heating, ventilation, air conditioning equipment, as well as other processes and other sectors. It generally includes at least dry bulb, wet bulb, dew point, and wind speed, and some coincident variables related to that. But the interesting part is the percentiles, and these are looked at the statistics based on the period of record, how many hours a year that it's going to be below a temperature, the 99.6, or above a temperature. And typical annual percentile used is 99.6 for heating and 1% for cooling. So 99.6 represents 35 hours that usually the temperature is going to be a little colder than that. 1% cooling means about 88 hours a year that it'll be warmer than that. But with buildings, a little bit of sizing differences are going to make that difference, particularly when we oversize our buildings to begin with. So depending on the application, how tightly you need to control temperature, humidity, you might use other percentiles or other variables. If you're doing dehumidification, you might be looking at dew point or wet bulb. Excuse me. Other percentiles are available for monthly. The ASHRAE handbook about 12 years ago, the cooling load chapter has recommended moving to monthly data. And one of the reasons there is, at least in the US, our fall period, your April period, I guess, is often a higher load period because the sun angles are lower and you're getting more direct penetration. The same is true here for us in the US in September, October timeframe. So you may have a higher monthly load. The 5% monthly is about equivalent to the 1% annual dry bulb. The best source is still the ASHRAE handbook. Chapter 14 has data on 9,200 locations around the world. It has data through 2019, which is the most recent. The good part is we're finally capturing some of that extremes, 2016, 17, 18, 19, which were not in the previous handbook. Continues to grow. We've had 1,000 more stations in the 2017 handbook. They have done several studies, and I'll show you one of the things they're doing on each of the locations in a little bit. But for the 2009 handbook, they did some comparison of 1,200 locations that had been in older handbooks and newer handbooks and looked at them. And what they were already seeing was a 99.6 dry bulb temperature was increasing by 1.5 degrees, and the cooling dry bulb increased by about 0.8. So that was already visible in the record. But it's not consistent. This is from the 2017 handbook and taking a look at the trends. And we are seeing a slight shift on an annual basis to increase the average and the max for the stations. But you see we have a range of from minus 0.2 to plus 0.2 for this. So quite a range there. The 2021 handbook has really good coverage in North America. I'd say decent in South America because most of the population is more on the coast or in the south. Europe is extremely well covered. Asia, pretty good, although there's some gaps there in the mountains, of course, north of India. But if you look at Africa, there really is a real lack of weather stations there. In fact, the largest economy, which is kind of around the crook of Africa, Nigeria, had until recently, this is the first handbook we've had any design data for that. And you see many other countries just don't have any. There's a tool that's available from ASHRAE, which allows you to get to the data and look at it in various pieces. So this pops up, you see circles with numbers. That's how many stations are kind of in that range or nearby. I can zoom into Brazil and begin to see more stations for that. I can zoom in once more to Santa Catarina and look at there, and we have 2 stations, one there for Florianópolis Airport. So that's, once we get there, I can begin to look at the data. And alongside allows you to do statistics with that, or do comparatives, or all the other bits and pieces for that. Or you can just get the traditional one-page summary of the statistics, the design conditions. So here's the one from Florianópolis, and let's look at it in a bit more detail because it's too small to read here. But the top part has the annual heating, dehumidification, and ventilation design conditions. So there's our percentiles for heating dry bulb. Similarly for humidification, coldest month, etc. And then there's the annual cooling, dehumidification, and enthalpy design conditions. And again, we have percentiles, and We have cooling, we have evaporation, we have dehumidification, and enthalpy, all as separate different looks at that. The last section for the annual is the extreme annual, and these are statistically based values based on statistics, not so much on projections. And you see extreme annual conditions there. Return year, you could expect to see temperatures up to 40 degrees in Florianópolis. That's not a prediction, that's just based on the data and the statistics, the return period. If we go on to the monthly, now we have the annual data that we had before, but we also have it by every month. So temperatures, degree days, wind speed average, precipitation, average, max, min, and a standard deviation. Then here comes the percentiles for the monthly design dry bulb, as well as the monthly design wet bulb, and a mean temperature daily range by month. So you can begin to look at some of the comparisons there. The last two parts for calculating design loads, we have the clear sky solar irradiance values there by month, but we also have the all sky radiation, so you can see what those values look like. The last part, the historical trends, is somewhat new. In many of the presentations I do when I'm pulling this up, we'll start to see at a station or the region at the 1% dry bulb, we may see a small difference. At a presentation I did yesterday for the Turkish chapter, it had about a half a degree visible already within the cooling 1 percentile. I mentioned some of the satellite data. NASA Power has been producing tables like this that they can replicate essentially, and this is an out-of-date page, and I apologize for that, but they can replicate those design conditions that I showed you from the ASHRAE handbook from the satellite data. It's pretty accurate, as it says there, about a half a degree and a half a degree Celsius, but also a half a degree latitude and longitude. They've got data going back to 2001 and can taking that forward, and there's the URL you can capture for that. If we're talking about data that we need to do a building performance simulation, we need to have something there for simulating representative performance. And typical meteorological year methodology, which evolved over the 70s and 80s, is the most widely used today. It's a composite of months. They don't all have to be from the same year, that are each representative for whatever period they're looking at. There's an ISO standard that uses the same method. There's often a little bit different weighting. Some people may weight solar more if they're trying to look at solar radiation, particularly for photovoltaics or solar thermal, or more evenly between temperature, humidity, solar, and just to get an average for that. It's just using a statistical indice of daily min, max, and mean for dry bulb temperature, wind speed, and global and direct solar radiation. So that's one thing you can do for that. There already are TMY type data sets. They are best for comparison. So if you've got two options, how do they compare? They're not trying to predict energy use. They're often used in complying with building standards or green building rating systems points. They don't tend to have the extreme conditions. They're representative, not the extremes for that. And they don't necessarily cover the design conditions, so they have a tendency to be mild. There are many TMY weather data sets available. I point out the INMET and TRY, the test reference years there for Brazil and a few locations in Antarctica. There's also a relatively new data set, TMYX, which has 16,000 locations globally. And I'll show you a little bit more about that later. And the data for that is very up to date. Some of these other data sets are getting quite old. The one used in the US frequently, TMY3, the data is now 18 years out of date, meaning we don't have any data newer than 2005. So actual weather data, you need it sometimes. If you're trying to do a retrofit of a building, you want to create a model that models what's going on, simulates what's happening now. I need to have a few years to be able to calibrate against that. There's sources for that today. Some you can get near real-time data prediction. The NOAA's National Center for Environmental Information collects data from around the world. Weather bank, weather source, whether underground or for fee. You can often get data from your national meteorological offices. They provide some of their data, not all of it, to the WMO data center. But the biggest issue with any of these data that are just providing data is how complete are they? Does it include what we need for energy simulate, temperature, humidity, wind, solar radiation? So here's an example, and this is the one location I've had where I can get continuous data over the last 85 years. This is actually just about 10 kilometers away from my house here in Washington, D.C., and they have data, complete data from 1938 to present. There are no gaps in there, no missing data, and that's unusual. There's some locations in Europe that have hourly data dating back into the early 1930s, but with World War II, there were a lot of 2, 3, 4-year gaps in the data flow. But this is really just to show you what happens. This is a small office building being simulated, each actual year data and what's happening. The last one is the TMY. Now, remember what I said, they tend to be representative. They're not representing the highs or the lows, but they are sitting about in the middle, not quite a median, but they are covering the range that's going on there. And the variation you're getting is some years will be hot summers and maybe mild winters, or other cases cold winters and hot summers. And several of the outliers you'll see are that. So what's happening with climate? The past 5 years are the warmest on record. In the fundamentals, they're only updated every 4 years, and as I mentioned, we only just got those 4 hottest years that have come into the data set. And the TMY data sets are updated infrequently. So took a look at 12 locations to see whether it mattered from the design conditions, also the TMY data. These include some of the older US locations, TRY, TMY, TMY2 and 3, as well as the IWEC data from ASHRAE and IWEC2 updated in 2010, and the TMYX, the new data set. This one only included data through 2018 at that point. So taking a look at the TMY type files, what's happening here? And if you look about 3/4 of the way over, you'll see Sao Paulo, and seeing in most cases a small drop in heating degree demand, heating degree days being the measure here, pretty consistently over all locations. We have the extreme cold, which is resolute above the Arctic Circle, and then we have Singapore, which has no heating degree days to speak of. But every location is been moving there. Cooling degree days, looking at the same thing, we're seeing that opposite trend, and a trend in increases. The one outlier is Winnipeg there in Canada, and I'm not quite sure why. There was actually a small decrease for that, and that's interesting. But pretty much every other locations, we've got Buenos Aires, Cairo, Denver, London, Gatwick, and Heathrow, Los Angeles, Madrid, resolute again, New Delhi, Sao Paulo, Singapore, Washington, and Winnipeg. So let's take a look at how the heating design conditions have changed. And what you see here is this is from 0. So we have the lightest color is the oldest data, the 1997 handbook, and then the most recent is the 2021. So what you'll see there, if we go look at Sao Paulo, we see it's the heating design conditions have increased from 10 to about 11 in Sao Paulo. And I know there's not a lot of heating done in Sao Paulo, but that's just to show you the variation there. You can see almost all of the locations are seeing an increase. Here in Washington, D.C., our heating design temperature used to be 10, and now we're looking at about, minus 10. Now we're looking at 8, minus 8. So almost all locations we did see that change. If we look at cooling again, starting at 0, now we're seeing kind of that variation. Sao Paulo has gone from about 32 to 33 over that time frame. If we're looking at Washington Dulles, we went from about 34 to 35, 36 degrees. And you see some variation throughout, that we are getting increases for each of the locations. Some of the hottest are getting hotter. Singapore there, from about 33, 34 up to 35, 36. So it is changing already. If we look at the impact on energy use for that, what we begin to see are some interesting trends. You look at Sao Paulo, almost no change there. And that's because there was a little bit of change in the cooling. But take a look at Resolute, which is the tallest bars there, right next to Sao Paulo, and you see a huge decrease in the red, or the heating. And that's pretty traditionally what we see, is that we're seeing a decrease in red and a smaller increase in cooling. If we take it to Singapore, it does mean about a small increase overall. If we look at Washington Dulles, near where I live, the heating is decreasing more than the cooling's increase. So we're actually getting smaller energy use, which is an interesting change. But it kind of varies depending on how extreme the climates are. You see London's almost flat. Los Angeles, which is predominantly cooling, increased slightly. Madrid, New Delhi, of course, being a hot climate. Buenos Aires kind of changed, but slightly higher for that particular. If we look just at the change in heating and cooling, we see a energy use change. Washington Dulles, very clearly you can see the drop in heating and the small increase in cooling. Sao Paulo, same sort of thing. Resolute, big drop in heating. Delhi, big increase in cooling. LA, Madrid all show that. Buenos Aires as well. Winnipeg is kind of one of the outliers, and I don't know why it's not showing more. Another thing that happens is heat island. And in 2018, the National Oceanographic and Atmospheric Administration, the same guys who have the climate data, did a measurement of what the heat island was in Washington, D.C. And so this is a map of the area. There's a small yellow pin to the left. That's Washington Dulles, I mentioned. Toward the center, under the word Washington, you'll see another pin. That's Washington National Airport, where I had that long period of record. And what they found was that it was quite a bit different. That between the heart of the city, where sidewalks, pavement, very few trees, buildings were all in place, we were getting temperatures that varied to parks, and that blue area there, kind of in the on the left-hand side, is a national park within the city, and you see the same sort of thing along the river. A temperature difference between those spots and the hottest parts in the city was about 10 degrees C. It's that much difference, that heat island. Now that's at a particular time of day. So we can't measure future data, so we have to go about creating it. There are 4 primary methods for doing that. There are 2 that are very computer intensive, downscaling, which takes these global climate models that have 1 degree by 1 degree data and bring that down to a smaller scale. That's pretty computer intensive. Statistical use statistics to try to look at what the probability of future data might be. Also very computer intensive. The one used most often, one I'll show you, is going to be time series adjustment. But there's analog scenarios. You try to find a location that is like today, like what your location's projected to have weather-wise in the future. It's often pretty easy. So this is from a paper there. This is, of course, U.S., North America, trying to look at how those are going to change. And you see, mostly we're seeing locations get hotter, to hotter, more humid locations. This is, for example, coming from from Michigan, and looking at a particular location. It's going to be more like the East Coast, so it's going to be warmer. In this case, it says 2.8 degrees warmer and wetter than the traditional summers there. So similar analogs can be done for that. I don't have a nice easy tool to do that for you, but I'll tell you what I think is going to happen. The IPCC has scenarios or storylines that really represent the range of what's going on. These are updated. The last assessment report, AR5, the fifth assessment report, was released 2013. We're waiting on the newest one, AR6, to be released anytime. These emission scenarios or storylines are called representative concentration pathways, and they have various numbers there. They're not exactly the climate change amount, but they represent everything from decarbonization, doing the best we can at 2.6, to not doing anything with 8.5. And here's the range of what they predict. There are different models going on here. You see, even on the right side, 2.6, there's a range of what various models predict, and so on through the variation. So there is a lot already available, but you see the change being predicted here is up to about 4 degrees Celsius. So the morphing technique, essentially you take an existing weather file and you take from the RCPs what's happened, the average monthly temperature change, a diurnal temperature change, how's the daily highs and lows changing throughout, any cloud cover to see what happens, solar radiation, any precipitation as well. And that results in this. The yellow is an existing dry bulb temperature. This happens to be Los Angeles in November. And you see it kind of gets down to 12 at night and up to about 20, 21 during the day. Nice location. But then there are 4 lines. Those are the different RCPs represented. And what we've got is a base diurnal daily temperature range. We have a scenario temperature range, which is often less. And then we have a nighttime temperature remaining higher, which is also seems to be a feature of that, along with the scenario delta T. So several things going on. It's not just adding X degrees to a particular thing. So there is some morphing and stretching going on. Similarly, heat island on an annual average is roughly about 1 to 5 degrees C. It varies quite a bit. I show the example there that it was over 10 degrees Washington, D.C. on a hot summer day, but that's not what happens annually. And it seems to be a function of city population beyond 5 million. It's roughly 5 degrees C. So the more hard surfaces that are storing data. It tends to depress daytime temperature and raises nighttime temperature, not unlike what the climate change models are showing. So this is Washington Dulles again, spring day, April 10th. The yellow again representing is the measured data for that. And then there are 2 lines, the 1 and 5 degrees. It has slightly lower daytime temperatures, and that's the measurements and the models show that overall. But the temperatures remain higher and stay higher after sunset and on till sunrise. So you see that bigger gap is nighttime. That diurnal temperature is less.